Hi everyone, I'm Sai Avinash. Welcome to Codeverse. I'm working as an SRE at Google Dublin. I'm already rank 3 at CodeChef. I'm master at Codeforces. I previously interned at Uber, and I'm also a Snackdown finalist. The subjects that I take are discrete mathematics, dynamic programming, graphs, and a lot of other competitive programming topics. Use the code SciLive to get 10% off on the Unacademy Plus subscription. So what do you get with the Unacademy Plus subscription? You get to interact with India's best programmers. There are going to be interactive live classes, and the doubt support is going to be immense. Like if you're learning a topic, if you have doubts on the topic, you can get it cleared with the doubt support, teaching assistants, and so on. And to top it all off, you can apply the theory in practice with the practice problems at CodeChef bot. So use the code SciLive to get 10% off on the Unacademy Plus subscription. So there are going to be new batches on Unacademy, starting from Mahayodha. It's a 2-month master course on advanced programming topics. It goes live on 6th July. There's Ekalavya, which is a complete course on Java programming for beginners. It's an 8-month durated course. This goes live on 6th July too. And there's another course, Brahmastra 2.0. It's an exclusive 5-month learning track for college off-campus placements. This goes live on 6th July as well. It's a 5-month durated course. So if you think it's all going to be useful to you, I suggest you to click the subscribe button and like and share it too. So I'll be starting the topic as well. So the topic for today is calculating GCD of two numbers using the Euclidean algorithm. So first of all, what's GCD? GCD. It's the greatest common divisor. As the name suggests, GCD is divided for two numbers, a comma b. It's the largest positive integer which divides both a and b, meaning GCD of 21, 30. So 3 is the largest number which divides both 21 and 30. Got it? GCD of 21, 22 is 1 because there's no number more than 1 which divides both 21 and 22. Okay. Got it. Now we got this clear. So let's discuss properties of GCDs before actually thinking of computing what GCD is, just to get you a feel of what GCD is, okay? So GCD can be, we saw one interpretation of GCD. What's another interpretation of GCD? We've heard about prime factors, right? Prime numbers. What's a prime number? A number which is indivisible. And it's not 1 as well. 1 is indivisible too, but it's not a prime number. It has only 2 distinct factors. So GCD of two numbers. Say we're calculating GCD of 84 and GCD of 210. Now 210 is a bit of a bad example. 63. Cool. Okay. Now we write the prime factorization of 84. 84 is equal to, that's 3 into 28, right? 3 into 28 is 2 square into 7. 2 square into 3 into 7. What's 63? It's just 3 square into 7. 7 per 1. I just write 1 on top. GCD for each prime number involved. So GCD is equal to, just write the prime numbers involved. Or you can do it in two ways. I'll tell you one way. Like the other way is obvious too. 3 into 7. And on top of that, write the minimum power in both of them. You can write this as 2 power 0, right? Minimum of 0 and 2, which is 0. Minimum of 2 and 1, 1. Minimum of 1 and 1, 1. Meaning minimum of each of the powers in each prime factors, you're going to put it on top of the prime factors. It's as simple as that. Got it? Yeah. So why are we doing that? Because GCD has to be a factor of both 63 and 84. And for that to happen, each prime factor का power जो है, like the power of the prime factor should be divisible by this and this. That's why we're taking the minimum of both of them. We can't take anything more than that. This is like, we can't take 2 power 1, for example. Because if we take 2 power 1, it won't divide 63. But it'll divide 84, but it won't divide 63. GCD should be the largest number which divides both of them. That's why between these two, whichever is higher, you take that only. Okay, easy. 3 to the power 1 and 3 to the power 2. We take 3 to the power 1. Because if we take 3 to the power 2, it won't divide 84. 9 is not divisible. 9 is not a factor of 84. 9 is a factor of 63. That's why you need to take only minimum. 7 to the power 1, 7 to the power 1. Okay. Write down each prime factor. And you see the corresponding powers in those two numbers. We take whichever is less of them and multiply them. That's 21. So 21 into 4 is 84. 21 into 3 is 63. Very simple. Another fun interpretation, just to get a feel of GCD. This is going to be fun, sir. GCD of two numbers, say 8, 6, or rather 8, 2. No, not even 8, 2. 8, 4 would be a better idea. 8, 4. So, draw 8 points on the board. Start from this point and go 4 steps. Draw 8 points and go 4 steps. 1, 2, 3, 4, and mark this. Keep doing this till you already reach a point. 1, 2, 3, 4. So gap between the points is the GCD. You might be a little confused. Like 8, 4 has only 2 points. So how did you generalize? Let's take a better example. GCD of 10, 4. Okay. Let's draw 10 points. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. What did we decide? We mark on point. We go 4 steps. 1, 2, 3, 4. Fourth step. 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 You can see that the gap between each point is equal for all points. And that gap is 2. And 2 is also the GCD of this. That's another way to look at GCD. You draw like whichever number is higher. Or you can do it with lower as well, but that's a different story. We'll just look at the simple version. Whichever number is higher, for example, 10 is the case here. Draw 10 points. Start from the first point, and with 4 points, by skipping 4 points, like the fourth point you mark it. Then the fourth point you mark it again. You keep doing that till you visit an already marked point. Like we did, we went here, went here, we went here, we went here, we went here, we went here. You can see the star forming, but that's a different story. But yeah, we do it till we reach an already visited number. And we can see that the gap between all numbers is same. And that gap is the GCD. Okay, that gap is the GCD. Let's look at another number. Like if the GCD is 1, what happens? GCD of 7, 3. 1, 2, 3, 5, 6, 7. 1. Skip 1, skip 1, skip 2, skip 1, 2. We go from here, we go from here. Did you see that? All points were marked here. And the gap is just 1. We got the GCD of 1. So this is a cool interpretation of GCD. You can visualize GCD this way. It can be useful in some problems, but this is a fun interpretation of GCD. Got it? So we looked at 3 interpretations of GCD. Now, how do you calculate GCD quickly? How do you calculate GCD quickly? So, GCD of A and B. We can see that GCD of A and B, this is same as GCD of A comma A minus B, right? Or alternatively, assume A is greater than B. This is same as A minus B comma B. Fair. Because if a number divides A, if a number divides A and if a number divides B, then it will divide A minus B and B. So the GCD, whatever is there, that GCD will divide A, the GCD divides B, and it's going to divide A minus B as well. And if you work out, it's going to work the other way around too. Got it? Got it? This is the main axiom. So GCD of A comma B is going to be equal to GCD of A minus B comma B. If you want to like verify it, take an example. GCD of 24 comma let's take a number 10. This is also same as GCD of 14 comma 10. See, and it's going to work because the GCD divides A and the GCD divides B. It's going to divide A minus B and B as well. It's very simple. So we established that GCD of A comma B is equal to GCD of A minus B comma B, where A is greater than B. One more thing. GCD of 0 comma X is equal to X. Okay? Why? Because X into 0 equals 0 and X into 1 equals 1. X into 1 equals X. So X can be the largest integer. X is the largest integer, in fact, which divides both 0 and X. Got it? So we are using these two axioms, these two rules, to compute the GCD quickly. So GCD of A comma B equals GCD, handwriting is bad sometimes, A minus B comma B. Alright, where A is greater than B. We can further write it like, you can also write this as GCD of A minus 2B comma B. And we can keep doing this while A is greater than B. Right? Awesome. So what can we write it as? GCD of A comma B is equal to GCD of A minus B comma B. And from this, if you keep doing this recursively, like what we from A, we remove the largest multiple of B we can while making it positive. And that is going to be A minus KB comma B. What is the largest multiple of B you can remove from A? A minus KB greater than equal to 0. You need to find the largest such K, right? Essentially. So that we keep doing this. K less than or equal to B by A. Meaning K is the largest integer less than or equal to B by A. Which means K is floor of B by A. Got it? So, which means GCD of A comma B is equal to GCD of A minus floor of B by A, floor of A by B into B comma B. Alright, simple, fair. Now what is A minus floor of A by B into B? What is this? This is essentially A modulo B. The remainder when A is divided by B. Like you're reminding the largest multiple of B from A. That means you're left with the remainder, right? It's as simple as that. Meaning GCD A comma B equals GCD of A modulo B comma B. Awesome. And this is like totally sufficient to calculate GCD very quickly. So let's write the code for this, pseudocode for this. GCD A comma B. Here we are assuming A is greater than 0. A is greater than B, sorry. Is greater than or equal to B. Because if it isn't, we can swap them and call the same function. So if B equals 0, return A. Else, return GCD of B comma A modulo B. And that's it. And turns out this is done in log of n, O of log n. Log n, or you can say log of min of A comma B, whichever, anything works. Log, we can say B here because B is less than A. Got it? Fair. Awesome. Now, GCD of B comma A modulo B. Now, how do you know that this program terminates? Like how do you know this won't go in an infinite loop? Let's see. Look at the second parameter, B. Now, B is being replaced by A modulo B. We know that the remainder with B is always going to be less than B, right? That's how remainder is defined. The remainder is going to be from 0 to B minus 1. Fair. Awesome. That means when we have B, and then something is going to be less than B. The next function call is going to be less than B, and so on. So this function has to terminate somewhere. It can't go less than 0. Correct? For example, GCD of 7 comma 12. We assume that A is greater than B, so we'll take 12 comma 7. This is going to call GCD of 7 comma, what is 12 modulo 7? 5. This is going to call GCD 5 comma 7 modulo 5, which is 2. And this is going to call GCD 2 comma, what is 5 modulo 2? 1. This is going to call GCD 2 modulo 1 is 0, like 2 leaves a remainder 0 modulo 1, right? So 0. That's going to be 1 comma 0. And then we are going to return the value 1. So we can see that 7 is becoming 5, 5 is becoming 4, 5 is becoming 2, 2 is becoming 1, and 1 is becoming 0. The second value is always decreasing. And if you notice, the first value is also decreasing, but let's just focus on the second value for now. It is always decreasing, ever decreasing. And when it becomes 0, we are going to return the first value, A. We are going to return A directly. That is our GCD. Got it? Yeah. So now let's go back to the code. What's happening here? We wrote the exact same thing that we discussed. Pseudocode directly convert kiya aur kuch nahi. A and B, we are returning A if GCD, this is the base case of the recursion as we discussed, no? When there's a recursion, there should always be a base case. Drink some water because I'm fumbling. There should always be a base case when there's recursion. So this is the recursive call. So GCD A comma B calls GCD B comma A modulo B. And we are going down the stack like one function after another. And at the very base case, when B becomes 0, we return A. That's it. If you want to get a better feel, I suggest you to try out examples, and I'll try out another one right now in front of you. So, a GCD which is not 1. For example, I'll take 16 comma 12. This is going to get over quick. See, A is 16, B is 12. GCD of 16 comma 12 is, it's also GCD of 12 comma 16 modulo 12, which is 4. GCD of 12 comma 4 is 12 modulo 4, that is 0. and 4 comes directly here, 4 comma 0. Now that b is 0, we return a directly. A is 4 and 4 is the GCD, and that's what we return. Awesome. So what's happening here? We are returning a smaller, like we have a big problem. Now we're dividing into smaller problems. Like we have, say, GCD of 1003, 1432. Now we don't know how to solve this. How will we solve this? By using this recursive function. And we can do this really quickly. How? This should come here because A is bigger than B. I'll just erase it and write it again. 1423, 1003. GCD is going to be GCD. What is one? This will come here directly and 1003, and this modulo 1423 modulo 1003, which is 420. That's funny. 420. Yup. Now we have a smaller problem. So once we have a smaller problem, we can divide that into a smaller problem again till we reach the base case, very base case, which is b equals 0. And then we return a. Then we return it up and up and up. Like whatever, in the end we get GCD of something, comma 0. Then we return the answer here, returning the answer here, 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 then here. Then we return the final GCD. That's how it's done. Now, speaking about the complexity, it's funny, like the complexity is just O of log B. But it's hard to understand how. Like it's not very trivial. Let's speak about it. So GCD of A comma B. Alright, we're calculating that. One thing to note is that A comma B, if A is greater than B, then A modulo B will be less than or equal to A by 2. I think you can remove the equality, but that's still irrelevant. If this happens, if A is greater than B, A modulo B will be less than or equal to A by 2. For example, you take 8 modulo 3, you'll get 2. 5 modulo 3, you'll get 2, which is less than 2.5. 2 is also less than 8. 8 by 2, which is 4. 2 is less than 4. How does this happen? How does this happen? A is greater than B. What happens? A by 2. A modulo B is there, no? You're removing as much B as possible from A. Like, for example, you have 9. 9 modulo 4. You're removing 4 from 9 once. Removing 4 from 9 again till you get 1. You're squeezing as much B out of A as possible. Got it? Yeah. Now, why did we say that it's going to be less than A by 2? Like, why is A modulo B less than A by 2? Less than or equal to A by 2 if A is greater than B. Why is this happening? Let's prove by contradiction. Suppose A modulo B is greater than A by 2. Meaning, from A, we squished out a multiple of B. We removed a multiple of B, right? And after removing that multiple of B, the number is still greater than A by 2. That means we can remove another multiple of B, right? So we arrived at a contradiction, like, say X, we removed the number X, which is a multiple of B, like I'll just write it as KB, which is greater than A by 2. Meaning, KB is less than A by 2. This is what we get. Meaning B is less than A by 2. So if B is less than A by 2, it means that A modulo B is also less than A by 2. Why? Because A modulo B is always less than B. And B is less than A by 2. Pretty simple there. So what did we discover here? GCD of A comma B calls GCD of A modulo B comma A modulo B. And this in turn calls GCD of A modulo B comma B modulo. This is going to be a lot of verbose, but you need to understand this is very important. It might seem a bit boring, this part, but this is something very important. So you need to pay attention here. A modulo B. Got it? Fine. Now just look from here to here. A became A modulo B. B became B modulo something. B modulo A modulo B. We know that A is greater than B. So A became something which is less than A by 2. This part became less than A by 2. And this part, we know that B is greater than A modulo B. So this part also became less than B by 2. So after 2 steps, the parameters are getting halved or lesser even. So what this makes is, after 2 steps, A is becoming less than half, B is also becoming less than half of what it was. So how many times can you divide a number by 2? We discussed it in binary exponentiation. We can divide a number by 2 at most log n times. A number n by 2 log n times. Right? So it means that the function is going to happen at most log n times, O of log n times. Here n is basically B, O of log B times. Fair and straightforward. So this is the code. GCD of A comma B is, if B equals 0, it's going to be A. We discussed that is the ultimate base case. B is going to keep decreasing. It's going to keep halving itself or even lesser. So it has to reach the base case sometime. Otherwise, it's going to go into the GCD part, where you solve a smaller problem. You keep solving a smaller problem till you achieve the base case. Then you return the answer. That's what recursion is all about. Awesome. So we actually found out how to calculate it quickly in O of log B, log of minimum of the 2 numbers, which is really quick. Just bring some water. So let's look at an application of this concept. What is the problems here? A, B, X, Y, all of them are integers. So given A, B, C, solve for X, Y, where AX plus BY equals C. Where, got it? AX plus BY equals C. Now, how will you solve this? Like they're integers. So for example, say you have to solve 3x plus 4y equals 1. You can see that one solution is 3 into minus 1 comma 1. Got it? And another solution is maybe, I guess, minus 3 comma 2. And so on. There can be many solutions. That's totally fine. How do you find it for like large numbers like 721x plus 423y equals 1? This is the question. How will you solve it? It gets hard, right? You can't always substitute values. You can't always say this. Agar ye 3 hua to ye kya hoga? What will this be? I'll increase this by a little bit. Let's see what this happens. No, you can't do all that. It's going to be really complex. You cannot. You need a formal method to do it. Okay. Before that, let's look at the condition for which it won't happen and for what it will happen. AX plus BY equals C. You're given A comma B comma C, and you need to find some X and Y, some integer X and Y. All of them are integers. You need to find some X and Y which such that this condition is satisfied. And what is this like? This is a straight line, right? Maybe something like this. This is essentially asking you to find integer points on the straight line. Okay. Peace. So, how do you go about it? So, we have this. So let's discuss about a no condition. When will it not happen instead of when will it happen? This is more easier. So say a number divides A, a number divides B, then the same number divides B. Then C should also be divisible by that number, correct? So putting this in proper words, C should be divisible by GCD of A comma B. As simple as that. Because GCD of A comma B is the largest number which divides A, largest number which divides B, like both A and B, meaning you can take the GCD common over here, meaning which would imply that C should also be divisible by GCD of A comma B. If it is not divisible by A comma B, GCD of A comma B, then there is no solution at all. For example, you can take 4x plus 8y. GCD of this is 4 is equal to say 22. This will have no integer solutions because this is already a multiple of 4. But 22 is not a multiple of 4, so this will have no solutions. 210x plus 28y is equal to say 21. 21 only, take 21. This won't have integer solutions because this is even, this is even. This won't be even. Got it? As simple as that. So how do we like find it? How do you find the solution? It's pretty simple, turns out. But to come up with this, it's a bit tricky to come up with this. So what we do here is go back and see what we did in the Euclidean algorithm, Euclidean GCD algorithm. GCD of A comma B, we called GCD of B comma A modulo B, right? And we know that A modulo B is A minus floor of A by B into B. Okay, fair. So GCD, we've put it into a smaller problem, correct? So we'll try to put this problem also into a smaller problem, the linear integer equation problem, which is ax plus by. First we'll try to solve it for GCD. Then, since we know that C, the number C has to be a multiple of GCD, so say C is 3 into GCD. And for this solution, say we got 4 comma 5. We can multiply this number by 3, 12 comma 15, and we'll get it for C. Say the solution for GCD is 4 comma 5. Then the solution for C will be 12 comma 15. Just multiply the whole thing by 3. As simple as that. Got it? So we'll just solve it for ax plus by is equal to G, where G is equal to GCD A comma B. Fine. So what are we going to do here? Ax plus by equals C equals G. So we'll try to divide this into a smaller problem. Say we have the answer to bx plus A modulo B into y equals G. Say we have the answer to this problem. Can we get to this? You might ask, why are we doing this? We're doing this just to investigate the possibility of, does this smaller problem lead to somewhere? Will this solution lead somewhere? Okay, got it. So say the solution for this is x1 and y1. That means bx1 plus, say we found the solution to this, bx1 plus A modulo B into y1 is equal to G, meaning bx1 plus A minus A by B into, I'll just put curly braces so it's not confusing, into B into y1 is equal to G. G is the GCD, just to confirm. Now we just rearrange the terms. B into x1 minus floor of A by B into B plus A into y1 equals G. So if we have the solution for bx1 plus a modulo b into y1 equals g, we can directly find the solution for ax plus by equals g. How? Look at this part. This is the x part. This is the y part. How did we get this? Since x1 and y1 are solutions to this, from here we went here, and from here we went here, and we rearranged the terms to see what comes next to x and see what comes next to y. Got it? And that way we get the solutions for ax plus by plus g. So here the new x is equal to, what is your y1? Because a into x, a into x, right? So a into y1, x equals y1, and y is equal to x1, this part, x1 minus floor of a by b into b. So let's revise what happened here. So if we have the solutions to bx1 plus a modulo b into y1 is equal to g, then the solution for ax plus by plus c, ax plus by equals g, would be y1, we just, one sec, would be b minus, we wrote this as b into x1 minus floor of a by b into y1 plus a into y1 equals g. So this is our new x and this is our new y. So y is equal to y1, so y is equal to this part, because ax plus by. This part is same as this part. Since this is satisfying the solution, we know that this satisfies, x1, y1 satisfies this solution, meaning this would satisfy the solution. All right. So the new y would be x1 minus a by b into y1. The new x would be simply y1. That's it. So if you have the answer for a smaller problem, we have the answer for this problem as well. Got it? Let's look at the code now. So this is the GCD function. These are the x and y values. Okay. So this is the base case. Let's come to that later. So x1, y1 and x1 and y1 values are being propagated for the smaller function. So after this function is being computed, we now know what we now know. The new x1 and y1 will be satisfying this formula, which is x1 into a plus, so x1 into b here, x1 into b and y1 into a modulo b, plus y1 into a modulo b equals GCD. Got it? This satisfies this solution basically. This is what the function calculates. Now we apply the new transformation for the new part. Like, since we know the answer for e x1 plus a modulo b y1 equals g, we now want what is the solution for ax plus by plus c. Ax plus by equals g. If you have the solution for this, how do you go for the new solution for this? That's what we're doing here. So x1 and y1 are solutions for this. They're being passed as reference. So the values are being modified inside there. Now once we have the values of x1 and y1, we update this value. We return x is equal to y1 and the new y is equal to y1 minus y1 into a by b. A by b is the floor function as we discussed. The computer does when a integer a is like 7 by 3, it will become 2 and not 2.33. So the new transform value would be this. That way, we get the solution easily for, like, by solving for smaller subproblems From the smaller subproblem, we build up on top, like what would be the solution for this problem, like the bigger problem, like 100, comma 40. 100 plus 100x plus 40y, x into 100 plus y into 40 is equal to 10, assume. From here, we build a smaller, we try to compute it for a smaller problem. Like we try to compute it for 40, comma 20. And so on. But for this, there won't be a solution because GCD of 140 is 20 and 10 is not a part. So it won't be a solution. If you can see this, if you can see it closely, this is our GCD function. This is for computing our like solution for GCD. You can see that the codes are almost similar, right? Like we return, this function is going to return GCD, but it's going to fill in values of x and y which satisfy ax plus by equals GCD. Okay, fine. These functions are almost similar. We just added this extra part. Got it? Awesome. Now, like as we revised previously, how would we extend it for like bigger numbers? 3x plus 4y equals 1 ka solution mil gaya. How will you do for 3x plus 4y equals 11? Just multiply these x values by 11. It's as simple as that. For this, x value would be minus 1 and y value would be 1. For this solution will be minus 11 and plus 11. That's it. Very simple. So that's it, friends. I hope you understood. Like, if there are any doubts, please drop them in the comments. I'll try to address them. So see you in the next video. Thank you.